So this example is kind of neat because it asks a slightly different question. It's talking about the magnetic energy stored in the inductor. And of course, that means the potential energy stored in the magnetic field inside the inductor, which is created due to Faraday's law effect. So 5 microseconds after the switch is moved from A to B, the magnetic energy stored in the inductor has decreased by half. What is the value of the inductance L? So the only two things we know is that we're talking about a time of 5 microseconds, so we can write that down if we wish. So t equals 5.0 times 10 to the minus 6 seconds. We're trying to find the inductance L, and it's talking about magnetic energy. So why don't we write down what is the energy stored in an inductor? That feels like a good place to start in this problem. So energy stored in an inductor, UL, is equal to 1/2 the inductance times the current through the circuit squared. Okay, where could we go with this? Well, we actually know what the current in this kind of a circuit is. So if it starts at A, it means we have a solid circuit and the current is flowing around. So initially it's all charged up. And then when we flip it to B, then we get an RL circuit, and we know that it's slowly discharging, and we know that expression for the current. That current is I0 times e to the minus t over tau, where tau is equal to the time constant L over R. If we wanted to, we could figure out what that initial current is, because we know that initially we've got this circuit with the battery, and we could use our potential and our resistance and figure it out. Let's not figure it out just yet. Let's start this problem algebraically, just so we have fewer numbers to calculate. Okay, so let's put in this expression for current into our energy equation. So our energy over time then is 1/2 times L times I0 e to the minus t over tau, and that's all squared. So now I'm going to square both of these terms. I get 1/2 L I0 squared e to the minus 2 t over tau. The next thing I notice right here is that I have 1/2 times L times I0 squared. That has to be the initial stored energy, UL initial. So if total energy is 1/2 Li squared, the initial energy you'd have would be when I is equal to I0. So this term would be your total initial energy. So I'm going to fill that part into my equation. Okay, where am I going to go from here? Why don't I fill in my ULs on the other side too? Well, the next place I'm going to go is that it says that the magnetic energy stored in the inductor has decreased by half. So that means that at the time we're talking about, at our 5 microseconds, UL equals 1/2 of the initial energy, UL0. Let's fill that part in next. So 1/2 of UL0 equals UL0 e to the minus 2t over tau. I feel like we're getting somewhere now. We've got that initial energy on both sides. That can divide through. 1/2 equals e to the minus 2t over tau. The symbol on the bottom is a tau. It looks a little messy there. If I want to get to my tau term, remember I'd like to get tau because we're asked for the inductance, and the inductance is a part of the time constant term. So I'd like to get rid of this e. I'll take the natural log of both sides. Natural log of 1/2. Natural log of e to the minus 2t over tau is minus 2t over tau. So then tau is equal to minus 2t over the natural log of 1/2. Can fill in my time t, minus 2 times 5 times 10 to the minus 6 seconds divided by the natural log of 1/2 gives me a time constant tau of 1.44 times 10 to the minus 5 seconds. Now just to finish, I can say that I know that my time constant tau equals L over R, So L is equal to tau times R. So my R is 50 ohms. My tau I have just found up above. Gives us an inductance of the coil of 7.21 times 10 to the minus 4 henries. So starting off, it feels like you don't know very much, but if you just think about what the expression for the energy and current are, you can come to your answer pretty quickly.